Good afternoon, Professor Miner, and also friends in Europe, and also good evening, friends in Asia, and also good morning, friends in North America and South America. I think we just had an exciting day in the United States. So you guys are having the election. So now is time for a break to have some seminar. So today is our great honor to have Professor Stefan Miner to give the second seminar for the System Analytics Global Leaders Seminars series. But before I introduce Professor Miner, I wish to do some promotion for the upcoming events. So we have more. Let me see. I should. So now I can see the. Yes. Okay. So we will have more speakers in the coming weeks. We have Professor Wang Lihui, Professor Max Shan, Professor Ren Guo. So the next talk will be on November 18th, 2 weeks later. So by Professor Lihui Wang, and more confirmed speakers, including Professor Alexandra Dogu, Professor Stephen Newman, Professor Jianjuan Shi, and Professor Skimniarski. So please stay in tune, and then browse our websites for some updates. Okay, so now may I introduce Professor Stefan Miner. Professor Stefan Miner is a full professor for logistics and supply chain management at the School of Management, Technical University of Munich. His research interests are in global supply chain design, transportation optimization, and inventory management, and the work was published in many peer-reviewed journals, including Management Science, AMSOM, OR, POM, Transportation Science, Transportation Research Part B, EJOR, Computers and OR Spectrum. He serves on several editorial boards of logistics and operations journals. Currently, Professor Miner is the editor-in-chief of International Journal of Production Economics. Professor Miner is a fellow of the International Society for Inventory Research, as is currently vice chairman of the Scientific Advisory Board of the German Logistics Association, and a member of the Research Committee of the European Logistics Association. Today, he is going to talk about his research. The title is A Data-Driven Approach to Strategic Inventory Placement in Multi-echelon Networks. So this seminar, I also wish to acknowledge the Germany-Hong Kong Joint Research Scheme funded by DAAD and Hong Kong LGC. So actually this year, so we planned some exchange activities, but because of COVID-19, so we could not travel to visit each other. But still, the exchange activities are still ongoing. So for example, through this seminar. May I now invite Professor Miner to give his presentation. Thank you, Professor Miner. Join me welcoming Professor Miner. Thank you. Yeah, Professor Miner. Yeah, thank you.
Yeah, thank you, Professor Kur, for the nice introduction and also the invitation to present to this seminar. And thank you to the audience from all over the world to attend that early in the morning or that late in the night. And before I start using the opportunity to share our latest research with you, I was actually also given the opportunity to do a small advertisement in the beginning of the journal I'm currently working with, the International Journal of Production Economics. So this is, let's say, the free advertisement for those who don't know the journal yet, which I assume will be a minority because the journal, and this is also part of our strategy, is really meant to be international in terms of readership and authors. So really covering all regions of the world. And just to give you some information which is typically asked for when I present the journal is what about its size? Why should I publish in that journal? So I just want to give you a few KPIs. So over the last years, we had about 2,200 submissions every year. And what we publish previously in 12 volumes, now in online publishing mode, is about 300 papers per year. Now, impact factor, you all know, this is always seen to be relative, but we have been increasing the impact factor continuously over the years. And this year, for the first time, having an two-year impact factor larger than 5. Which makes us the number 4 on the ISI list in the area of operations research and management science, number 6 in industrial engineering, and number 9 in manufacturing engineering. So it's a safe Q1 journal in all the areas, which sometimes is important. And on Google Scholar ranking, it's actually number 2 in the area of operations research. Now, what is probably more important, what are the people running the journal? It's not only me, but we are also doing that in a really international team, which consists of Edwin Cheng from Hong Kong, which probably many of you will know, Peter Keller from Louisiana, Bart McCarthy from the United Kingdom, myself and Utang from Sweden. So we are handling really this broad area of production economics, and when submitting the paper, you will most likely deal with one of us. Now, what's most important is, of course, what is this journal all about? I mean, the journal has been around for more than 30 years. Of course, production economics sounds like a very traditional name. But of course, what we are proud of is that also advertising that in this audience here, it's a journal actually at the interface between engineering and management, right? It's not a pure econ journal. It's also not a pure engineering journal, but really at this interface. And there's a very broad interpretation of production and economics. So production in the broadest sense, production, logistics, service operations. And the economics is somewhat highlighting that we look after economic and financial evaluation of such technological developments of strategies. So whenever you ask yourself, is this the right journal? It should be a topic in the broadest sense on manufacturing and services, and at the same time have this valuation component. And even though I just mentioned the rankings that we are scoring well on operations research, and we are also very well interested in operations research submissions, you should always not forget about this valuation aspect, right? So tuning algorithms, there's definitely better journals who have a focus on that. And we are really looking for also practical manuscripts, interdisciplinary in nature, so you don't have to read everything, but I wanted just to highlight what's special about the journal. Of course, there should be an innovation and a contribution, but really this interdisciplinary, also broadest focus internationally, and not forgetting about this economic and financial consequences aspects. And what we are publishing is, of course, regular submissions under following this double-blind review process, but we also occasionally have special issues in different areas within the scope of the journal. And currently there is 3 open call for papers for special issues on various topics. The first one is on behavioral studies in sustainable supply chains. Now, of course, we are currently dealing with a lot of problems and challenges in resilience, in sustainability, and so on. And this is all in the core of the journal. This special issue in particular addresses this behavioral research in sustainable operations. Now, the second one, of course, if you have more detailed questions, you can ask George Wang, who is the managing guest editor of it, looking more into technological advances which have to do with the Internet of Things and cyber physical systems. So really pushing technologies and concepts and platform concepts forward on the digital twin and data-driven optimization in the physical internet. This is a special issue where you still have some time to submit. So we try to advertise that ahead of time. All these calls are also available on our homepage. I also copied the link here if you want to read a little bit more about the focus and who will be the guest editors handling that for us. And the last one is one at the interface between operations and finance. So again, here you see this interface between operations and the valuation and economics part, in particular for supply chain in the financial area and under new innovations in the financial scene. So that's what I wanted to share about the journal. And if there are any questions you might have, we could take them now or also later on in the Q&A. Just feel free to ask any questions or any concerns, or also take the liberty to reach out to me personally if in case you have suggestions or want to check about suitability of certain manuscripts for the journal. So that's the small advertisement block I wanted to use here. And then if there's no urgent questions or things to be discussed here, then let me move to my research presentation. This is actually a summary and some work in process on work we have done over the years under the area of data-driven optimization. And today I would like to focus on our work on data-driven optimization to inventory management and inventory placement. This is work, if I say we, I have been doing together with several PhD students over the years and also currently. So in particular, the work on multi-echelon networks is joint work with Josef Svoboda, who is a PhD student in my group. And what we really try to advertise and to do here is to bridge and bring new innovations from data science into the rather traditional world of supply chain or multi-echelon inventory systems and inventory theory. Now, what is the overall motivation? I guess all of you have seen this Gartner picture when it comes to analytics. And of course, in this seminar series, we all want to advertise our latest work in analytics with different applications. And usually, if I focus on the right-hand side of this picture, we usually talk about what will happen in the future. So more the forecasting part in predictive analytics. And then if we combine it with decision-making, talking about prescriptive analytics or optimization. And our philosophy of data-driven inventory management was somewhat getting into the field of not seeing those two tasks of forecasting and inventory optimization as two sequential tasks, but rather as an integrated task, because both the forecasting problem and the inventory placement and sizing problems are optimization problems. But still, the way at least we have done it traditionally, even though this is changing now and has been changing for the last years, is very often seen as two sequential tasks. So first do the data analysis, some forecasting, look at forecast error measures, and then use those as parameters for an inventory optimization. And I think this misses a lot of opportunities we now have with big data and going beyond time series kind of modeling of demand processes when it comes to inventories. And this is what I want to advertise in my presentation today. Now, over the years, we had a couple of applications. We actually started this project with in a joint work with Annalena Sachs on in a retail environment. So we were actually cooperating with a large retail chain who wanted to optimize their inventory ordering and also more get into automation of inventory ordering for perishable products. Now, perishable products have the challenge that inventory policy structures are quite demanding. There's lots of additional things you need to specify, not just how customers appreciate fresh food, and also how they will buy different products if there's different shelf ages on the shelf. But in particular here, it also heavily depends on prices, weather, so lots of external factors, which we are typically in very traditional inventories not looking at when we assume that demand follows a certain distribution, and we mostly fit those distributions on historical data, or even if we have forecasts, we are sometimes not bringing in all these big data information. And this is now where we already started with how can we enhance our forecasting models and also include optimization techniques in an integrated way to manage this trade-off between leftovers and stockouts, right? And in particular in the retail applications, on-shelf availability is a quite important topic, and not having enough inventory results very often in lost sales or substitution, and the amount of lost revenue. So here's just some numbers for some markets to say why is it important, is quite large. At the same time, the food lost by perishing items either at the store or retail level or even during manufacturing is quite a considerable amount, and becoming more sustainable. Of course, we want to improve inventory strategies in order to reduce the waste without having to compromise on service levels. Now, at the same time, we face other challenges, in particular in retail, that there is different demand profiles over day of the week and also hour of the day, depending on also where stores are located. To just explain this picture here, in Germany, stores are not open 24/7, right? So there's opening hours, and typically they're also closed on Sundays. There's a few extra challenges here, but what we wanted to take into account when it comes to this data-driven optimization is also including those sales patterns. So a lot of multivariate extra information when setting inventory levels and also when forecasting required inventory levels at various prices, competitor prices. So lots of features from big data to be taken into account. Now, how did we address that? To get you into the philosophy, and then I will report on how we rolled that out to a multi-product and multi-echelon systems. Now, the very traditional way we usually look at demand modeling in inventories is that we either already assume right away a theoretical distribution, or we connect inventory management to forecasting techniques. So first, do a forecast, look at forecast error measures, and then use that to parameterize distributions. Now, very often this is a kind of sequential task, and many factors like prices and weather might be taken into account when doing a multivariate forecast. But very often, if we do it the textbook way, we would use ordinary least squares, for example, for regression, where you might remember that ordinary least squares are penalizing overages and underages in a symmetric way, and also larger deviations of actual demand from a forecast in a kind of a quadratic way. Now, if you just remember the news vendor, you would say this is not what in inventory management we do in the news vendor, where we say usually shortages or stock outs might have larger penalties and leftovers, which is sometimes not true if it's, let's say, highly perishable food. In particular, if you're operating in discount retail at very small margins. For that reason, now we want to take into account an integrated way of doing the inventory decisions right away with the cost function or also revenue functions we have in mind. Now, second, there is also a strong correlation of sales with promotions and other features, really this feature dependency, and not building a new model whenever we are relaxing one assumptions on the demand management was another objective of this integrated data-driven modeling. And in other areas like spare parts, there is a lot of theory also available which says demand will depend on installed base usage. There might be sensor information on certain machines. So there's lots of extra big data, and we are having more and more opportunities technologically to get hands on that data. And now we also want to use that in our inventory target setting environment and objectives. Right, and the way we do it here is not like the traditional way, sequentially first do a forecasting problem and then solve an inventory problem. We also try to refrain from making parametric assumptions. So let's say, look at gamma distributed demand, normally distributed demand, negative binomial demand, but work on the data right away. Now, of course, some of you will say, isn't that what robust optimization and sample average approximation also does? Yes, the philosophy is the same. So treating historical demand observations as scenarios and then apply robust or sample average techniques. But that's now what we do in an integrated, non-parametric way, also bringing in extra feature information. Now, if we do that, and let me skip this one here, which is just a summary of knowledge of the distribution. So we also move in the direction of distribution-free approaches, where this has been also around for many, many decades. And we also abandon from knowing the parameters of the distribution, which also has been around. So we are heavily building on existing approaches, including, of course, using empirical distributions in robust optimization in stochastic programming, to just mention a few on this slide here. Now, when we try to combine estimation and optimization, we are moving away from this simple method of moments, but rather go into the direction of regression. And instead of using ordinary least squares, we are now using the objective function from the application. So besides the loss function in the forecasting exercise is already the loss function of the application. Of course, this has also been done before under the term of absolute regression, for example, if you would apply a news vendor kind of objective here, or also in other data-driven work. Now, what becomes important if you combine that with a standard regression model, and that's often overlooked, although I'm not claiming we are the first ones to do that here, is that there, when we do the estimation and look at the uncertainty about demand, that there is inherent demand uncertainty, but also uncertainty that comes from parameter estimation. And that's what we are now after. And let me first give you a brief glimpse for those who don't know that paper from Annalena Sachs' thesis on safety stock planning under causal demand forecasting, to give you an idea how this overall approach works. Now, here's a kind of an idealized picture how overall demand depends on, for example, the sales price. Now, usually, and also in the retail application, there were many more features, but just for illustrative purposes, we produced this picture where we synthetically generated some demand dependent on price. And then you would see, okay, everybody sees the straight line here, that of course demand is a downward sloping function of the sales price, but there's still variation around. And what we want to do here is now finding an inventory level. So not first of all predict the dependency between demand and price, but right away in these different data points and data observations, project an inventory function, which is then penalizing overages and underages from the true inventory application, and not just squared differences between the demand line and the demand observations. So this was, or this is the overall philosophy. And then what we're saying here, and now I'm getting you into the technicalities of the model. So you could say this is nothing else than with different notation, a kind of news vendor model with overages and underages. So whenever there is an inventory, we charge overage cost or a holding cost. And whenever there's an underage, so when demand is bigger than what we bring, then there is unsatisfied demand. But what we are now doing here, and this is the way we do the combination. So let me just get my pen here. So our order quantity is this term, right? We would say all these X are big data explanatory variables. This can be weather, this can be prices, this can be competitor prices, but this could also be lagged demand. So say if I want to rebuild a kind of an ARIMA process here, I can bring in features of historical demands, and then I weight those different features X with an estimator beta. So you would say this beta times X, looking over all the different M explanatory variables, is what we typically do in regression. Right? If we do a multivariate regression, this term I circled here would be demand is equal to this combination of weighted features, and we would estimate the beta. Right? So this would be our regression exercise. Now what we are doing here in this integrated model is, let's assume this beta times X is our order quantity. And whenever this circle term here is bigger than the demand, then of course we have inventory Y. Now in the opposite case, we cannot sell more than what we bring. And now this term here, this data-driven term, is not our demand forecast, but this is already the hypothetical inventory level we would set under feature data. And this is where the integration comes into play. So we are not separating, estimating the betas to do a single point forecast, but we are saying we are expressing our final decision inventory level already as a function of external data. And what this then does here is we are managing the trade-off between overages and underages in the objective. And then for each historical demand observation, so all the n different demand observations from the past we are taking, and in hindsight saying what would have been the best compromise, not just looking at demand and inventory, but at the specific features we had in a certain period, thereby accounting for, was the price higher or lower? What was the weather that day? Were there special promotions or were there special advertisements behind certain demands? And thereby we want to try to reduce the overall unexplained variance of the demands. And what you're seeing here is, hopefully, we are now optimizing over both the inventory parameters, so sales and inventory leftovers, but also about the beta, right? So the estimation here of the different weights of the external factors become part of this integrated model. And the nice thing about this model here, this is a pure linear program, right? You can put it to whatever is your most favorite linear programming solver. And even for big data sets, it works very fast. So this was the overall idea, and you could also do it for service levels. like non-stock out probability or fill rate. Another good thing here is you can do it in a multi-product version where they are sharing shelf space. So you could say you don't need a new inventory model once somebody introduces capacities to it, because now we have a linear program. And if we want to make it multi-product, it's adding another index, and bringing in capacities is bringing in another constraint, right? So the toolbox, in the end, we are reducing our optimization problem to an integrated linear program. Gives us a quite powerful toolbox and is easy to adjust, whereas when we look at traditional stochastic inventory models, bringing in such a thing like a capacity constraint sometimes requires redoing considerable parts of the machinery. Now, of course, there's also some downturns here. So first of all, we were assuming this linear relationship with the features. Right, so of course you could say I did not specify what X is, so this could also be the square root of a price or the squared price or whatsoever, and there could also be interaction features. But like many of these exercises, the feature engineering is a quite important task, and with the ambition to make things linear, sometimes we are of course might lose against deep learning approaches who are the way they are built more easily picking up nonlinear phenomena. This might, let's say, be a challenge in here. So then we tested that on synthetical data and also on case study data with this retail chain. And let me just briefly show that here, but all the details are in the paper I mentioned. This outperforms this sequential ordinary least squares and then inventory optimization, and also the combination with any other method of moments estimation techniques. Of course, and this is now what many of you know, big data approaches work if you have lots of data. Now, if you only have a few data points, like let's say 20 demand observations, of course, there's still quite some noise in the optimization here. And results are getting more robust and more reliable the more historical data samples you have. So if we move from 20 to 50 to 100, so that's quite important. So for small data approaches, of course, the generalizability of this approach still has some challenges, and their traditional approaches like fitting theoretical distributions, which then generalize right away, might be competitive or better. But once we have all these different features and sufficient amount of data, this approach works quite well. Now, this was the basics, and now I want to come to the multi-echelon systems, which is then based on work with Florian Taube and Josef Svoboda. So the first one was an extension now to a very simple multi-echelon system. So one warehouse, multiple store system where the stores are composed of a back room and the original shelves. And the particular challenge here, or also what makes this data-driven approach quite attractive, is that we are not just optimizing inventory levels for multiple products in multiple stores, but that we can also optimize delivery patterns, right? So not necessarily every product is replenished every day. So using the capability of mixed integer programs, we can now actually optimize for the pattern that certain parts of the assortment are replenished every day, like perishables in the previous application. But some of them might also only be replenished on Tuesdays and Fridays. And then we get this repeated pattern. And for those of you who worked in inventory models and in multi-echelon inventory models, looking at approaches which have different review periods at different stages or throughout the week are quite challenging. And we are now addressing that here by making the pattern optimization. So what are the days where I'm replenishing a certain product? Part of the data-driven optimization, of course, then we are losing the linear programming structure, but moving to a mixed integer linear program, like in a lot sizing problem, saying these are the days, or this is the days of a pattern every second day or every Tuesday and Friday. But we are heavily then benefiting from capabilities of solvers that can still solve mixed integer linear programs of this kind quite efficiently. Now, the idea we applied here is similar. So for all the different products, we are assigning a target inventory level, again, a composition of weighted features, and we are also learning those features and the weights from the data. And on top of that, we put in the replenishment patterns, which means if certain products are always replenished in the same pattern over the weeks, and then propagate those demands to the central warehouse, it also impacts how we are setting the target inventory levels at the warehouse. So that's the idea here we have been pursuing. And what we want here, and to take the bridge again to a robust optimization, we want a robust pattern on replenishment days for certain parts of the assortment. So it's again a kind of a compromise. How do we set those replenishment patterns? And for a given pattern, also taking into account that then inventory levels have to be enough for the next 2 or next 3 days when the next replenishment is actually up for replenishment. So as I already said, what we're doing here, and I just want to give you a high-level overview how now the mixed integer program looks like, because otherwise it's just big lists of notations, which I'm going to skip. So what we have in the objective is, again, now the variable cost of delivery. So we are also having this transportation trade-off. Do we have a shipment every day or even twice a day, or are we shipping certain products only every second day? At the same time, have costs for inventory holding and shelf stacking. And what we had before, also the trade-off between setup costs, which would be here a major and a minor setup. But you could say if a certain store orders in the morning or in the afternoon, it will create a shipment. So a truck is going, and every product I'm including in that order in the multi-product context is then causing a minor setup cost for doing the packaging, the picking, also the picking from the back room to the shelf, and so on. So you could say what we're also modeling here is a kind of a feature of a joint replenishment problem under the ordering patterns. Now, the constraints are the basic constraints I have already shown in the model before. So we had constraints on demand satisfaction, so overages and underages, but also flow conservation, so inventory constraints, certain smoothing constraints. So you should not have most of the shelf restacking on Fridays and Saturdays, where it's mostly about sales and cashier operations. So have more of receiving shipments on days where sales are a bit lower, and also capacities on shelf space, back rooms, and so on. And as I said, what we are playing here is the capability of mixed integer linear programming, that we can bring in lots of these real world constraints under this data-driven environment. Now, the next slides, let me skip those ones here. This is just the formalization. And let me just discuss on a case study we did with this approach. So we did that, as I said, with a retail chain, which was looking at 66 of their stores, which were replenished from a single logistics distribution center. So we had been looking at multiple periods with, let's say, 4 weeks structure, and to limit it down here, we selected 10 products. So we were only looking at one kind of the assortment, not of the full assortment of those stores. And like in all these data-driven exercises, we were splitting the data into a training and into an evaluation set. And what you're seeing here in the numbers and the results is the savings we generated from this data-driven approach compared to a very sequential forecasting and inventory optimization approach, and also some genetic algorithm heuristics where we had solved the inventory and transportation problem sequentially before. So the savings here were quite considerable over a very brute, rule of thumb approach. Savings were about in the range of 30% here. So compared to a more sophisticated, still sequential approach, we still saved 3.7%. Now you might say, should I worry about saving 3.7%? But remember, this is discount retail, where sometimes margins are in the range of 2%. Right? So this does a lot to the margin if you're saving on overall cost 3 to 4%. So this was the second case, and now I want to get in the final part really on this multi-echelon, going beyond the two-stage optimization, where we also brought in this data-driven idea, but now also combine not just the inventory sizing, but also the inventory placement. This example here on the slide, which is not a pure distribution system, also not a pure assembly system, but maintains features we see usually in supply networks. So there might be some common parts. There could be some final demands which need to be served, but there is usually a general multi-echelon network behind the system. And the question is now, of course, there's lots of literature on multi-echelon systems going back to the early work of Clark and Scarf and Simpson. But all of these models, which have been the starting points in the late 50s or early 60s of the last century, were working with distributional assumptions. So they were assuming demand follows a certain distribution, which we know and where we also know the parameters, or like with Simpson's work, even assuming a normally distributed demand, or in later extensions, assuming bounded demand, where the challenge is then, how do I define demand bounds? And what we now believe we are adding to that literature, looking at into this guaranteed service model to begin with, is now not taking demand as a given with a theoretical distribution and then repeating those challenges of what's the right distribution, how do I estimate the parameters, but now do this safety stock sizing, but also the safety stock placement problem in a data-driven way. So following the same philosophy as before, we have historical data, we have feature data, and now can we solve that problem using the same data-driven philosophy. Now, here's a brief summary of the literature on a multi-echelon inventory review. What this work here is based on is the guaranteed service approach. So put forward or first suggested in this work by Simpson in 1958. And there have been lots of extensions by Sean Willems and Steve Graves over the years and other co-authors, such that this guaranteed service approach, which has the capability to solve large networks, whereas this so-called stochastic service approach, which is the extension of the Clark-Scarf work from 1960, is sometimes already getting numerically challenging when we're introducing more stages. Now, what this results in is typically a nonlinear optimization problem, right? So for all of those of you who work in the field of safety stock optimization, we usually get these K times sigma times square root of the lead time or the coverage period. So this square root then makes a problem nonlinear, and then either we can solve it with nonlinear solvers or exploit some structural properties like bang bang inventory policies and then use dynamic programming or spanning tree algorithms, or also successive approximation for the linearization. So lots of techniques have been tried out to deal with this very complex nonlinear optimization problem. Now, the structure this optimization problem has, and this is just for making this thread, it's highly nonlinear, right? So here we have the square root. So the optimization problem, this overall guaranteed service model typically results in is that we are minimizing the cost from safety stocks, right? So this is here then our safety stock cost. And this is in a square root way. This is one way, but there are other objectives also being nonlinear depending on this so-called coverage time in the system. Now, the good news is very often that the set of constraints here is linear. So if the nonlinear objective wouldn't be there, it would be a linear program. And that's now what we are trying to bring in with the data-driven approach. So now we are saying, where does this sigma times square root of t come from? It comes from aggregating demands over the lead time. And then depending on whether we assume independence of demands, or even if there is a correlation over time, we cannot typically avoid the square root. But now in the data-driven approach, we are now saying, let's use this guaranteed service optimization framework with really allocating safety stock placement over the system. And let's do that in the same data-driven way. And this is what I have on the next slide to give you an idea how we do that. So this is the way we get away from the square root. And this is also what releases from specifying what's the demand bound. So now we are implicitly, by data aggregation, determining those terms. So what we're assuming here, and I start with just a single or simple inventory system and then show you how it works for the big network. Let's assume we have historical demands as before. So there's a demand history over the past. And now from the past demands, we are actually building samples of aggregate demand, right? So if like here, we say if the lead time is 4 weeks, we get demand samples aggregating the first 4 demands, then aggregating the next 4 demands, aggregating always pairs of 4 demands. And if we do that in a linear program, we are just adding up those historical observations, potentially also taking into account feature information. And then for those sampled demands over the lead time, we apply the same data-driven approach as before, right? So this now gives us the opportunity to aggregate demands, get historical demands now as lead time demands. So we are playing the same trick, but now on lead time demand, and we are generating those lead time demands from the historical observations. Now, if we are moving now to a multi-echelon system, it works with the same philosophy, but now we have to aggregate demands from multiple retailers, so multiple retail stores, or in an assembly system here, we have to decide whether we want to put safety stock only at the final product level, or whether we also want to keep safety stocks at the component level. And this now determines whether I take this decision all at the end or safety stock allocation, that depending on this choice, which is an implicit choice of the guaranteed service model, we are building those demand samples according to, is the lead time here including the component lead time, or is it only the lead time for doing final assembly and all my different components have their own safety stock and can deliver with a 0 service time? Now, for those who are not familiar with the guaranteed service model, what we are saying here is I'm optimizing the pattern of where to put the safety stocks. So do I only put the safety stock at installation 3, or do I essentially put it everywhere? Or in bigger networks, really select those stock keeping units where I want to place safety stock. And if I have that given, I solve this demand aggregation. So what's really the demand over the lead time, where the lead times now are incoming lead times, which become decision variables, right? So we are bringing those ideas, pattern optimization. So how do I decompose the big network into a smaller network? And then for a given decomposition, do the safety stock sizing problem in one big mixed integer linear program. This then suggests a lot of decomposition techniques. So do the binary pattern optimization at the higher level and the inventory sizing and the sample aggregation at the lower level. And that's what we're then doing. So this either for assembly systems or the same also works for distribution systems, where then we are aggregating demands from different streams if we decide to pool at the central warehouse, right? So here we are then taking different demand samples from the same period and apply the same logic when optimizing for the centralized demand approach here. Now, the overall optimization problem looks maybe scary on first sight, but what we're doing is, again, nothing else with just blown up notation, what I did in the most simple news vendor data-driven fresh food retail application. So now over all my different locations in the network, I'm minimizing the cost of inventory. And now if you see that here, there's no longer a square root, right? So I'm accounting for the inventory level differently. And the way I do it here is I do the bookkeeping whenever my base stock inventory at every location is bigger than the demand from any sample I have, there will be inventory. In the opposite case, there will be a stock out. And then I'm counting stock outs, or I'm counting the magnitude of stock outs to actually do service level calculations here, right? So this is a kind of non-stock out probability measure here. So through the bookkeeping in this linear program, I can track different service levels and then put a constraint on that. And the only thing that makes life a little bit more difficult is then here the binary variables about the pattern optimization. So do I put safety stocks everywhere, or do I put safety stocks only at distinct locations? But again, if you look at the optimization problem here from its structure, if I write it down as a big problem, it's a mixed integer linear program. And if I want to put it into a decomposition structure, I could actually take the binaries, so the pattern decision variables to the upper level, the continuous variables to the lower level, and then apply Bender's decomposition, for example, or also any other integer programming technique. Now, numerically, we tested that. So far, as I said, this is still a work in progress. We have been playing around with very small systems. So if somebody is wondering, have we already solved the 36 real-world problems from Sean Willem's data set? The answer is no. So these are still too big for our method. So computation times are still a challenge. But what you're seeing here, if we are operating with 500 or 1500 demand samples for different holding cost structures, different lead time structures, we can actually solve this problem here, both for assembly systems and distribution systems. Of course, in the order of magnitude of minutes, right? So this is not seconds, but this is also not supposed to be a real-time inventory deployment problem, but rather a strategic safety stock placement. Where should I place those safety stocks? And what this data-driven approach then does in a purely synthetic environment is it gets the same order up to levels and the same patterns you would get from the analytical model under the guaranteed service approach, assuming gamma distributed demands or normally distributed demands, which for the moment is a kind of proof of concept. So we have done that for assembly and, as I said, distribution systems. There are some extreme cases, but usually it works pretty fast for different coefficients of demand variation, for fill rate constraints, for non-stock out probability constraints. And what we are currently working on here is solving that for bigger networks. So I think I'm still doing quite fine in time, but we also should reserve a bit more time for discussion and questions. So to sum up, what I tried to advertise is this integrated approach of forecasting and inventory, moving from very simple inventory systems like the news vendor to multi-period, multi-echelon, multi-product systems, still use capabilities of mixed integer programming solvers or advanced decomposition techniques, releasing us from making distributional assumptions and facing challenging parameter estimation problems. So really this data-driven, distribution-free approach, also accounting for external factors, so not purely historical demand data, which of course I have shown on the previous slides, but you could also combine it with external data and then follow this beta times X philosophy. And at least for smaller problems, and if there is sufficient data, this approach consistently outperforms other methods, in particular if data is censored or if demands are price and weather dependent. Now, limitations, as probably you might guess, the linear programs are getting quite big. So large problems are still a challenge, also for large data sets where more work on decomposition and probably also heuristics is needed. But of course, you also need to bear in mind what we have now integrated is multi-echelon, multi-product, or if we would combine that with dual sourcing, also multi-channel systems. So at least the framework and the philosophy is quite rich. Of course, numerical aspects, still lots of work to be done. And if you're interested, we will also be happy to cooperate if you have nice methods to also try them out on the data sets. So that's what I wanted to share. Thank you for the attention, and I will be happy to answer all kinds of questions.
Yeah, so thank you, Professor Stefan Miner. So it's now the Q&A section. So if you have question, I think on Zoom, so you can type your question. If you also wish to ask in person, then you let me know. Then I will unmute you, and you can show your camera as well. When you ask your question, then you may type your name and then also your affiliation. We will appreciate that. So I think there are a few questions. At the very beginning, I think there is a question from the chat box. So from Stephen Guangzhou. So what's the sensor mean here, Professor Miner? From the very beginning, I think this question. Yeah.
Let me see the questions here.
Yeah, from the chat board. Yeah. I think it's 10:20. That my time. Your time would be 3:20.
Yeah, I have it. So what does censored mean? Now, in the retail environment, if it's not online, you will not see demands, but typically you only see sales, right? So in the end, you get point of sale information. And this means whenever you are out of stock, you are not observing the true demand. So what would have been the demand if there would have been more inventory? Now, what we do here is, in that case, look at typical demand patterns, knowing there was an out of stock situation for inflating our sales to get a demand estimate. So censored here in this context means that we did not observe, and our data set in the retail application did not give us demands, but only sales. Now, of course, we did not account for inventory inaccuracy, which might also be an application if, let's say, for some data time series you are seeing abnormal demand or zero demand, even though you're supposed to see that, but that's more of a data exercise. So what we have done in the retail was just working with censored demand. So I hope that answers the question about the censoring.
Yeah, I think Stephen from Guangzhou, I think he has a follow-up question. So how do you decide on the length of the lead time and the amount of demands to aggregate? And how do variations in those times improve the results?
Yeah, that's a good question. So probably I was a bit too fast on that part. Let me go back here. Maybe to this picture. Now, usually you would say when we talk about lead times or transportation times or processing times, of course, these lead times are exogenous, right? So here I'm assuming that there is a lead time for getting the products to the central depot. And then there is a transportation time if the depot has sufficient inventory to ship it to location number 2 and location number 3. Now, if I look at that system, and if I would say there is no inventory at the central depot, then of course the lead time for both of those stores, so if they want 1 unit extra, and I need to size the safety stock here, would be L1 plus L2, and here it would be L1 plus L3. So it would be the total cumulative lead time through the system. Now, what happens if the central depot has plenty of inventory? Right, so in the framework and philosophy of the guaranteed service approach, so what happens if this stock point here can deliver right away? It only means the delay for store number 2 and store number 3 is the shipping time. So in that case, it would only be L2, or here it would only be L3. Right, and that's also what we are mimicking here on the right-hand side. So between deciding for a service time, so an outgoing service time of 0, or the entire initial lead time, I can decide. And this is like in the guaranteed service approach, I'm deciding about the service time. If I have a huge safety stock, I have a service time of 0, so I can serve any request from my inventory. Now, in the worst case, if I don't keep any inventory, and now I receive an order, I have to wait for my own replenishment lead time. And what we are now deciding, like in the guaranteed service model, we are deciding about the service time. I'm now setting this binary indicator between 0 and T1. So with this binary indicator, I'm actually deciding the split of the total system lead time between the central depot and the retail stores. Of course, you see here, if the lead time is long, or if you make your time scale too granular, this comes at a price of lots of binary variables. Now, once I have this binary variable gamma set here, then for this split, I'm doing the demand aggregation. So is it the demand aggregation over the last L1 plus L2 periods, or is it only the aggregation over L2, right? And this is then what you see here. So the demand aggregations under a certain decision will be taken based on how I split the overall lead time. So that's a kind of implicit aggregation based on how I decide to split the entire lead time through the system, which is exogenous, into the different parts. So you could say this is a kind of how I do the set partitioning of the total lead time into certain parts, like we do in the guaranteed service approach. And now we're achieving that through setting a binary variable. And based on that pattern, I do the demand aggregation in a second step. So I hope that gave a better idea on how we are doing that.
Yes, thank you, Professor Miner. We have another question from Peng Shu. So do you assume that there is a manager overseeing the entire supply chain network so that he has all the information to optimize the entire network?
Yes, so what we're following here is a centralized approach, right? So saying what we are optimizing is what we can optimize under the control of one IT system or one integrated system, right? So this is not a decentralized system with potentially asymmetric information. So this is still the very traditional one decision maker, full information kind of approach.
Yeah. So from Paul, so he noticed that simulation is mentioned. So may we know that which part in this research use simulation?
We use simulation actually for validating the approach, right? So in some parts we have worked with real data from the retail chain, but of course to first do a proof of concept, we were synthetically generating demands from normal and gamma distributions. So we sample some demands for training our data-driven approach. Let's say we take 20 demands or 50 demands or 100 demands, which we show to the method for training the inventory levels and the inventory pattern. And then from the same distribution, we generate more demands out of sample to see whether it really achieves the service level and what costs it will achieve out of sample. So simulation is really the in-sample training to generate the synthetic demands, and out of sample for the evaluation, right? Whenever we don't base it on the real data set and then do the split into the training, validation and evaluation data set, we use simulation for the controlled experiment here.
Okay. Yeah, so thank you very much, Professor Mina. So we do have actually everyone. So you may type your question in the Q&A box. So we have a question from Zixin Xu. So does the analytical solution available, does the optimality of safety stock policy holds under for bullwhip effect? Also, how to resolve the computation cost of the large LP?
Now, as I said, the larger these mixed integer programmings are getting, there is of course a challenge. So this then will require some kind of heuristics. So you could actually on the binary part of the patterns apply some math heuristics. But we are currently trying to work on exact methods to decompose the big system into smaller ones and then also optimize for subsystems. So that's hopefully I'm answering that for the computational part. And the first part was on analytical results. So where do I see that? So my chat, where did you get the question about the analytical results?
I think it's in the Q&A. So the yeah. So answered. So
okay, no,
answered. Yeah.
In the yeah, okay, there. Now, of course, saying products change dynamically and frequently. Now, this is actually what we try to account for here by saying we don't use the demand as a kind of time series, but try to bring in other features. Of course, this somewhat requires that you pick the right features and of course also do a retraining of this network. So you could say, I would not use the entire demand history, but then also put weights on historical demands to really give higher weights to more recent demand observations. So what I presented here, and to be honest, with the developments we are currently doing, we don't have that yet, right? So we still make some implicit assumptions on the demand history for the aggregation. So we hope to be able to pick up on dynamic changes by let's say, bringing in trend factors, for example, what we see in the demands. So with the aggregation I've shown yet, this is not built in, but we have some ideas on this feature-based consideration to bring in seasonal factors, trends, and also changes in customer behavior. Now, of course, the challenge is if you only have limited data, then of course there's quite some variance and variation in the outcome here, right? So with making other assumptions about uncertainty sets to bridge it to the robust world, there would be other opportunities to do here, but we haven't included that yet.
Yeah. So thank you, Professor Mina. I think you just answered Yi Cai from Hong Kong UIMSE, so about the robust global supply chain network. Yeah, so the next question, yeah, I think you answered that question, right? Yi Cai.
Yeah, I think there's another one now on the COVID-19.
Yes.
How does that change with if we have structural breaks? Now, saying that all the demand history we have might be somewhat not very informative if we see a surge in demand on some retail products and disruption on supply in other areas, right? So we haven't really looked into stochastic lead times yet, not even including disruption scenarios, because these are even, and we hope still it remains a less frequent kind of thing we are observing. But like with many methods, if you have structural breaks in your demand time series, that's not included, even though, of course, you could say from the data, if you observe that there is a kind of new structure, you could set a flag and then do something different. But this is the same challenge we would also face in all other inventory models. If your past is not representative, how representative is your data for making projections and inventory recommendations for the future? I think I don't really have a good answer for this one here, besides saying it's challenging.
Okay, yeah, so thank you, Professor Mina. I think we have a question from the chat box from Ray. So for the data sets used for this study, do you need to pre-process that as there may be some noise data? Thank you, Professor Mina. Another question is about the extension of the proposed model for other products, such as electronic devices. What would be adjusted in the model?
Now, of course, the adjustment would be if we have more data from electronic devices or sensors. When we do the demand aggregation, we are not taking the demands as we have seen them, but we also need to bring the features as I have shown in the beginning, right? So then we would set the inventory levels not just as a base stock, but those base stocks maybe let me just go back to the slides here. Right, so here I was assuming I'm just setting a base stock and I'm comparing the base stock next to the demand. So then I would change the B here as a function of all my sensor and device data. Right, so that would be working similar to the simple news vendor model I have shown in the beginning. But there was another question about the data set and the pre-processing. Now, of course, what we have been doing here as a pre-processing for the retail data was a kind of correction for missing values and outliers. So we haven't automated that or integrated that into the decision model here, right? So we are not automatically setting a flag for outliers. So this would still give a challenge in here.
Okay, yeah. So are there any further questions? Yeah, feel free to let us know. Okay, so for me, Professor Mina, I also have a question. Because your framework, so it's a data-driven framework. When we think about data, so I always have a question. So how do we know we have sufficient data? So so how do we determine the sample size in your framework?
Yeah, so far we do it, let's say, by experimentation, right? So in the synthetic test, we see that sometimes 20 data points are not enough. Sometimes also 100 are not enough, depending also what kind of service level you are using. I guess we all know that non-stock out probability is quite sensitive. If you have seen some stock outs, to recover from that, so that you get a long range average. But we haven't endogenized the choice of data, right? So far also for the training, we are saying we are using that many data points for the training and that many for the evaluation. Although, of course, there is some methods from machine learning which are somewhat endogenizing the weights on historical data or what part of the history to include, but that's, let's say, not part of the framework yet. Even though I agree it's a very important aspect, because if you just take it for granted and you have too little data, it might give you the wrong suggestions for inventory levels and also for the wrong placement, right? So what we have experienced in the beginning here, if we work with too little data, the approach would not be capable of correctly picking up pooling opportunities, right? So to identify pooling opportunities, in particular in distribution systems, you need some more data points, but no automation on that yet.
Okay, so I see Oscar has raised a hand. So now I would like to allow Oscar to talk. Oscar, are you here? Oscar, if Oscar is preparing, I may help. Peng Shu has a follow-up question. Is it possible to apply this framework to a decentralized system? Any benefits we can obtain from this extension?
Now, decentralized would mean there is, let's say, two companies, one buyer, one supplier, for example. Of course, the challenge, like also in many of the stylized models on decentralized system, is how to get the game theory part into the picture. Now, of course, what is around in the mathematical programming literature, including games, would be if it's a sequential decentralized system, so you have a clear leader-follower structure, then to formulate this as a bi-level programming problem. Right, so what we typically do in the analytical work for a decentralized system with a leader-follower structure, so modeling as a kind of a Stuckelberg game, the mathematical programming along would be a bi-level approach. Now, if you have simultaneous play, so a more balanced power structure and more looking into kind of a Nash equilibria, this would require us to solve mathematical programming games, like, for example, if we have integers here, integer programming games. And as already said, honestly, computation times are already an issue. And if you put normal form games and game theoretical concepts on top of this, even if it would just be sequential play in the bi-level, this would considerably add to the computational problems. Now, from the philosophy, if you say you regard that as two mixed integer programs which are played simultaneously between two parts of the supply chain or sequentially, like in a bi-level game, conceptually, you would be able to write that down. Numerically, it will be adding to the challenge which is already there.
Okay. Yeah. So thank you, Professor Mina. May I invite Oscar to talk? Are you going to ask a question? Oscar, are you here? Okay. So maybe Oscar, you are away. Okay. Then okay. So we have one more question from the Q&A box. So hi, Professor. Thank you for your presentation. May I know how to control the data-driven issues, let's say overfitting, sample error, model misspecification under the supply chain or network? From Lin Shaocheng.
Yeah, so what I have shown so far was just taking an objective function where we take the features like prices, demands, or just historical demand observations. Of course, what you could do is to avoid overfitting, to penalize the too frequent or too large use of certain features. So for example, adding penalty terms like we usually do in lasso or rich regression, thereby avoiding part of the overfitting that you assign away to every feature I'm offering to the model. Also the same, if I have lots of samples, then two old samples, I might get different weights. So also using some kind of kernel approaches here. So we haven't tried that out yet, but the first thing to try would be the traditional machinery from machine learning and data-driven approaches to also control for overfitting.
Okay. Yeah, so are there any further questions? If no, may I thank again Professor Mina for the very insightful presentation. I also wish to take this opportunity to thank the organizing committee for the hard work, and also all the participants. I know in Asia now is almost 11:30. Thank you for joining us. So before I end this seminar, I wish to have a reminder. Okay, so we will have the next seminar. I hope all of you can join us again on November 18th. So the time this time, the next seminar will be 10 o'clock. 8 o'clock in the evening, Hong Kong time. So probably it's 2 hours earlier. So please pay attention. So it's it's still 10. Sorry, I'm sorry. So it's still 10. So the same time. Okay, it's still 10. So same time, Wednesday, November 18th. Okay, so a seminar by Professor Li Hui Wang. So thank you all of you for joining us. So good evening, good afternoon, and good morning. Okay, so thank you. See you next time.
Okay, thank you so much, Professor Mina, for your support. And thank you, Dr. Kuo, for organizing this. See you next time.
See you. Thank you.
Thank you.
See you. Bye.
Bye-bye.
Bye-bye.